So the same steps that we're going to follow here on this one will be similar to what you do anytime you have a Verilog and you have to come up with a state diagram. You just kind of look at the big picture and you can see that this has only 3 states, A, B, and C. So that's not so bad. I can go ahead and draw my states A, B, and C. I can see from my second always block that my reset state is A, so I can go ahead and do that. And then I just want to look at my cases to determine what happens with each state. So I can see that when I'm looking at state A, it says if R. So R is my input. R is going to tell me what to do. So if R is 1, then my next state is C, and my output is 0. So now I know this is a Mealy machine because my output depends on my input. So we just saw that if R was 1, my next state was C, and my output is 0. Now, if you want to just really have a shortcut way of writing it, you can do that, where the thing before the slash is your input and the thing after the slash is your output. If you have more than one input, you probably need to label them. Another way, this is not important for this test because I don't think I see Dr. Trahan doing this, but another way that it is often done is by putting the Boolean value like R. So if R was 1, it'd be 0. And if it was not R, I would put like a slash on it. But I don't think y'all ever do it that way, do you? Have you? Okay. If any of you ever grow up to be the Digital Logic SI, the other professor does it that way sometimes. But I'm not planning on giving up my job. Okay. All right, and then it says, so that was if A was 1, if R was 1, and it says else the next state is C, and our output, next state is C no matter what, but if R is 0, our output is 1. So we still go to C, but we have 0, 1. And now for B, if R, our next state is A. So for B, if R is 1, our next state is A. And it said our output was 1. And then for B, our else, so this would be if R is 0, our next state is C. And our output is 1. And now I'll go to state C. If R is 1, my output is B. I'm sorry, my next state is B, and my output is 0. And else, if R is 0, my output is A. My next state is A, and my output is 0. And that's it. Okay, any questions on that? The state, because it was a parameter up here. Actually, no, never. Oh, it looks like it is a typo. So good question. I copied this from an old test for homework. Let's see. S, this should be probably should be not necessary. Yeah, I don't think we need that. So I think probably when he wrote this, he probably was copying the code from something else and then just didn't take that part out. So did not catch that, so that was a good catch. Any other questions? All right, so going on to problem 5. So for problem 5, I am going to do this one all the way out. I might not do problem 6 all the way out with deriving the minimal Boolean expressions for the next state to be input to the flip-flops, because that part takes a while. So I might not do that for the next one, but I will do it at least for this one. Okay, so here we have a state table, and then we're given a state assignment where we have A equals 0, 0, B equals 1, 1, C equals 1, 0, and we need to do the state assign table. Now, when you do a state assign table, you need to make sure that you account for all the different possibilities. If I'm using 2 bits, 0, 0, 1, 1, 1, 0, I need to make sure that I have something for all 4 possibilities. If I had 3 bits, I'd need to make sure I had something for all 8 possibilities. So I'll have my present state and my next state, W equals 0, W equals 1, and output Z. So A is supposed to be 0, 0. And the next state, if W equals 0, is C, which is supposed to be 1, 0. And if W is 1, it's A, which is 0, 0. And the output is going to be the same. B is 1, 1. I'm going to put that at the bottom, just so I'm going to do them in order. That's B in numerical order. So if W is 0, my next state is B. Oh, wait, no, sorry. Yes, this is what I'm doing. So I'm going to write them in here so that I don't get confused. B is 1, 1, A is 0, 0, C is 1, 0. Now that I have those, I can just copy them. So for B, which is 1, 1, the next state when W is 0 is 0, 0. When W is 1, it's 1, 1. And my output is 1. And C is 1, 0. And its next state, if W is 0, is 1, 1. And if W is 1, it is also 1, 1. And our output is 0. And then, that should have been in this row. I don't have to put these in order. I don't know. I just kind of feel compelled to do so. And then I'll have my don't cares, which is 0, 1, because that's the 2-bit combination that's not used. So this is my present state. I'll call this Y1 and Y0. And my next state, I'll have a capital Y1, capital Y0. So each bit, if I were to draw the whole circuit out, I don't have to draw the whole circuit, but I do have to come up with the expressions, is a flip-flop. And so I'll start with Y1. And Y1 has as inputs since I'm having eraser problems, I won't do that. It has as inputs little y1 and little y0 and also w. So my Carnot map will look like this. And I'm doing the Carnot map for capital Y1. So I'm going to start with my first row, and my first row corresponds to when W is 0. So that's this column right here. So when W is 0 and Y1, Y0 is 0, 0, I get a 1. I get a don't care for 0, 1. And I also get a 1 for 1, 0. I get a 0 for 1, 1. And then W equals 1 is this bottom row. And I get a 0 for 0, 0. A don't care for 0, 1. And 1s for the other two. And it looks like this is my best. So Y1 equals Y0 bar W bar or Y1 W. While y'all are copying that, I'm going to try to erase. It really does not want me to select the pencil. Okay, now I'll do Y0. So the same inputs. Y1, Y0, and W. And so Y0 is the second column here. And so when W is 0, I see I get a 0. For 0, 1, I get a don't care. For 1, 1, I get a 0. And for 1, 0, I get a 1. And then when W is 1, that's over here, I get a 0 for 0, 0. I get a don't care for 0, 1. And I get 1s for the other two. And it looks like that would be this. So Y0 equals Y1, Y0 bar, or Y1 W. And then the last thing I need to do is to get the expression for my output. Since it's a Moore machine, it doesn't depend on the inputs, so it only depends on the state that it's in, so it only depends on y1 and y0. So I have this cute little Carnot map with just two variables, 0, 1, 0, 1. And I have a 1 for 0, 0, a don't care for 0, 1, a 0 for 1, 0, and a 1 for 1, 1. So my output Z equals Y1 bar or Y0. Questions on that? Yes. So here's how it would look. The question was for Zoom people, if this was a Mealy machine, what would be different? I'm just making up these values. This has nothing to do with the current machine. So your state table would have these are just completely made up, has nothing to do with anything. Your state table on your output would have separate columns for W equals 0 and W equals 1, which means your Boolean expression when I would go to do this would have would be as I'd have to use my 4x2 Carnot map. So I would have Y1, Y0, and W here, and so it would just be bigger like that. And it is also possible you can have more than one output. So you could have something that looks like this output. W equals 0, W equals 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 1, 1, 1, 0, 1, 1. So if you have an output that looks like that, that means your output is has 2 bits to it. So let's say that it said output was capital S. You would have an S1 and an S0. And you would have to come up with the expressions for each one of those separately, just like we did Y1 and Y0 separately. Other questions? All right.
Could you go back to the output of Y1, Y0?
Is this where you need to be?
Yeah, the smaller,
The little red one, or
yeah, the smaller output, yeah.
yeah. Did I make a mistake? Anybody? Okay. Did you have a question on it, or did you just want me to explain it? Or did you
Oh,
just
no,
need to get
I
it?
just needed to see
You
it
just
for a
need to see it.
second.
Okay. You need to make the noise that Zoom makes when someone leaves so that I know that my heart is breaking.
Like,
Yeah. Yeah.
oh, sorry about
Yeah.
that.
All right. So go on to problem 6. Design a 2-bit counter that when f equals 1 counts in the repeating sequence 0, 1, 3, and when f equals 0 counts in the reverse direction. Use D flip-flops. Construct a state diagram or state table. Specify a state assignment. Construct the state assign table. Derive minimal Boolean expressions for flip-flop inputs and circuit outputs. Okay. All right. So what do you think our states are going to be? Just imagine this is where you can use like your experience in the lab. Imagine you were doing this and you needed it to display on the little 7-segment thing or with the LEDs the numbers 0, 1, and 3, or and when you press the clock button it should go to the next one. What do you think the states would be? Yeah. I would have 3 states. For right now, I'm going to call them 0, 1, and 3, with that actually being my output. So my output, I'll just actually write that on there. I'll just call it S. And it does not say, but we should pick one of these to be a reset. Which one would you like to be the reset? I think so. I usually start counting with 0 or 1. Alright, and when f is 1, it should go forward, and when f is 0, it should go backwards. So if f is 1, I should go in this direction. I'm going to actually write f equals 1 this time, just because it makes it clearer to me in my head. And if f is 0, I should go backwards. So I have my 2 possibilities for state 0, and then for state 1, this would be f equals 1, and f equals 0. And for state 3, f equals 0, and f equals 1. Alright, so now we need to do a state assignment. So I'll just call this one 0, 0, this one 0, 1, and this one 1, 0. That's just arbitrary. I have to use 2 bits because I've got 3 numbers. If I only had 2 states, I could just use 0 and 1, but I've got more than that. So I'll have my state table. And I'll have, now I actually do need to say what my output is, and I'm going to have my output, I was originally thinking of it as a 7-segment display, but I don't want to come up with what those are, so I'm going to have my output also be a 2-bit number. So my output, I'll call it Z, will equal 2B00, 2B01, 2B11. So just the values for 0, 1, and 3. So I didn't need a box. So I have my present state, my next state, and my output. So I've got 0, 0, 0, 1, 1, 0, and 1, 1. And my next state for f equals 0 and f equals 1. My output, this is a Moore machine, so it does not depend on f. How do I know it's a Moore machine?
Yeah, it was depending on the state. It doesn't depend on the input.
Right. So this is an example where my output is also 2 bits. So my next state for 0, 0 is, with f equals 0, is 1, 0 and 0, 1, and my output is 0, 0. And for 0, 1, it would be 0, 0 and 1, 0 and 0, 1 and 0, 1, 0, 0, 1, 1. Don't care, don't care, don't care, don't care, don't care, don't care. And then we would go through and do the Boolean expressions the way we did in the last problem.
Why is the output of the state 3? 1, 1.
Because what I'm outputting is the value 3. And so that's why. So all I would do next is say this is y0 or y1, y0, y1, y0, and s1 and s0, and come up with the expressions for those. But I'm not going to do that unless we get done and nobody wants to leave and everybody says, oh, let's go back and do some more Carnot maps.
Are counters always Moore machines?
I wouldn't think they'd have to be.
How do you decide that it should be a Moore? Just reading that.
It's just the way I wanted to do. You could have done this a different way. So the way I thought about it was the way I actually just said out loud. I was imagining actually doing this in the lab, and that's kind of how I would have done it.
Okay, thank you.
Don't forget to make the Zoom noise as you leave. Okay, any other questions?
So, I don't get that next state. Like when f is 0,
So,
where you go to 1,
okay,
0, 1.
so the problem was that I didn't label these. I tried to skip a step because I'm lazy. So I should have done this first. This is A, B, and C. So my next state, so f equals 0 and f equals 1. So if f equals 0, I go backwards, so from A I go to C, and if f equals 1, I go forward to B. From B, if f equals 0, I go backward to A. If f equals 1, I go forward to C. From C, if f equals 0, I go backward to B, and if f equals 1, I go forward to A. And then I made the assignment. I said A equals 0, 0, B equals 0, 1, and C equals 1, 0. So then I just went through and replaced all these letters with their assignments. and that's where these came from. So these numbers here, are really just kind of arbitrary. They're just labels. They don't mean 1, 2, 3. And so I think that's what was confusing you, because over here I said this number meant 3.
No, I copied the F0 going to the first bit. Just copied
Oh, okay, but you understand now?
Yeah.
Okay, all right. Any other questions? All right, so I'm gonna start a new recording before I go on.